Hey everybody. What an interesting time to take calculus. But you've made it. You've made it to Unit 3. Unit 3 is covering the last part of Chapter 3, which is hyperbolic functions, and then heading into Chapter 4, which is applications of differentiation. It's a lot of neat stuff. Starting off with hyperbolic trigonometric functions, we're going to look at these functions that you may not have seen before. These are the trig functions that are created with hyperbolas. So if you look over here at this picture, you can see here we have this hyperbola, okay, and this hyperbola here, and this is a base hyperbola where we've got x squared minus y squared equals 1. And this reference angle right here is a over 2, and we have the sinh and the cosh. Okay, so the sinh and the cosh, and if we want to find those, here are the formulas that we are going to use. So if we're trying to find the sinh of x, and this is pronounced sinh, if we're trying to find the sinh of x, what we have to do is we have to take e to the power of x, subtract from that e to the power of negative x, and then divide that by 2. Okay. If we're trying to find the cosh of x, okay, and this one's pronounced the way it's written, you're actually going to use a formula very similar to the sinh, but we are adding my e to the x and e to the negative x, and then dividing by 2. This next one, the tanh, can be defined as the sinh over the cosh. So this can be defined as the sinh of x over the cosh of x, or e to the x minus e to the negative x divided by e to the x plus e to the negative x. All right, the cosecant is the reciprocal of the sinh, so you would just flip this fraction here. And the secant is the reciprocal of the cosh. And the cotang is the reciprocal of the tanh. And I always want to write it that way. Let's practice first by evaluating these. So we're not doing any calculus, we're just noticing this. Okay, so keep in mind, like when we first got introduced to trigonometry, right? We would figure out what the sine of pi over 2 was, right? We learned how to plug that in and evaluate it, and we would get the sine of pi over 2 is going to give me 1. All right, so let's do the same thing here. Let's figure out what the sinh is of 0. So when we do that, what we're doing is we're evaluating this sinh formula for when x is equal to 0. So the sinh here, if I'm plugging in x equals 0, I'm going to have e to the 0 minus e to the negative 0 all over 2. And I end up with 1 minus 1 over 2, which is 0, because 0 divided by 2 is 0. All right, let's do this with a cosh. So I have the cosh of x, the cosh of the natural log of 5. So I'm going to do my work with x being equal to the natural log of 5. Remember that the formula for the cosh is e to the x plus e to the negative x divided by 2. So when I plug this into the formula, I'm going to have e to the natural log of 5 plus e to the negative natural log of 5, all divided by 2. Now, using our rules of exponents and logarithms, e to the power of natural log of 5, that's going to cancel to just be 5. All right. Now this one, I'm going to write a couple steps here. Keep in mind that if I have a negative in front of a logarithm, that means this negative comes up here as a power. This is that power rule of logarithms. We've talked about this in previous lectures. So if I have 5 to the negative 1, that's like saying the natural log of negative 5, or sorry, the natural log of 1 over 5th. Then my e and my natural log cancel each other, and I'm going to end up with 5 plus 1/5 over 2. Well, if I add 5 and 1/5, I'm going to end up with 26/5. You divide that by 2. And then that's actually 26/10, but I can reduce it to 13/5. Here are some identities of hyperbolic trig functions. And let's go ahead and prove them. Remember how we prove identities? You basically manipulate one side to try to get it to be equal to the other. Or you manipulate both sides to try to get them to be equal to each other, but you never cross sides. Remember when you're proving identities, think of that equal sign as like a barrier, okay? But specifically, one you never cross. So I'm going to use the more complicated left side here, and I'm going to prove that it's equal to this less complicated right side here. So I'm going to take the cosh of x and subtract from it the sinh of x. The cosh of x is equal to e to the x plus e to the negative x all over 2. Now we subtract from that the sinh. And the sinh is the one with the minus. Now the next thing I'm going to do is I'm going to distribute out this negative sign here so I don't have to worry about sign errors. And that turns this one negative and this one positive. The next thing I'm going to do is I am going to split up these numerators. So I'm going to distribute the denominator of 2 to each piece. Once I split it all up, I'll see that I have an opportunity to cancel some things. Specifically, my e to the x's will cancel each other. And then I'm just left with these two. And if I add those together, I'm going to get the other side of the identity. Because 1/2 plus another half is 1. So my value is going to be e to the x. And then I've shown that that left side, you can see that left side, well, let me write in this corner, is equal to the right side. All right. Let's do the same thing with letter B. The only difference is going to be that I'm going to manipulate both sides. So my left side here, I'm going to do that first. So if I'm doing sinh of x plus y, that would be like saying e to the x plus y minus e to the negative x plus y all over 2. All right, now let's manipulate the right-hand side. So the right-hand side's more complicated. So I'm going to have the sinh of x times the cosh of y. So the sinh of x is going to be e to the x minus e to the negative x all over 2. And then the cosh of y is going to be e to the y plus e to the negative y all over 2. And I'm going to add to that the cosh of x, so e to the x plus e to the negative x over 2, times the sinh of y, see if I can squeeze that in the side here, e to the y minus e to the negative y all over 2. All right, now let's simplify that right-hand side. All right, now I'm going to simplify these products. Now, let me write down just a couple of hints here. Note what you're doing. Up here, you are foiling. Okay, you're foiling those. And then you got to simplify it. So the 2 times the 2, that's no big deal. That's the 4. Notice I quickly wrote that down. When I'm foiling, I'm going to have the following. I'm going to have e to the x times e to the y. Well, when I multiply like bases, I add their exponents. Fuck this shit. So when I FOIL it, I'm going to multiply my e to the x times e to the y, and that's going to be e to the x plus y, because remember, I multiply like bases, add their exponents. E to the x times e to the negative y, I'm going to have plus e to the x minus y, and then I'm done FOILing this out, and then I'm going to have negative e to the negative x times e to the y. This is going to give me negative e to the negative x plus y. And then negative e to the negative x times positive e to the negative y is going to give me negative e to the negative x minus y. And I'm going to FOIL similarly for the second one. It's a little squished on the end here. So let's see if I can fit all of that in. It's going to be longer. So I'm going to have e to the x plus y minus e to the x minus y plus e to the negative x plus y. And I'm running out of room, plus a negative e to the negative x minus y. And this is all over 4. Let me move this over. Okay, let's simplify some things. Notice that quite a few things cancel. Basically, my e to the x minus y's are going to cancel here. And my negative e to the negative x plus y cancels here. And the other two are like terms. So I'm going to have 2 e to the x plus y minus 2 e to the negative x minus y over 4. Now, a couple things I can do here now is the 2, 2, and 4. I can cancel a factor of 2. And then here, I can factor out the negative. What I'm going to end up with is e to the x plus y minus e to the negative x plus y all over 2. And notice, here's my left-hand side, that's equal, or that was my right-hand side, and that's equal to my left-hand side. Excellent, huh? Okay, so let's consider some limits of these hyperbolic trigonometric functions. Because these things are defined in terms of e to the x and e to the negative x, it really helps us to look at what happens when x approaches infinity or negative infinity. So here, if I have the limit of e to the x as x approaches infinity, this really is just going to be like e to the infinity, and that's infinity. If I'm going to do the limit of e to the x as x approaches negative infinity, this actually, think about this for a moment. If I have e to the x, but my x is a negative infinity, this would be like saying 1 over e to the infinity, which is like saying 1 over infinity. And if I have one piece of cake and infinitely many pieces I'm going to try to cut it up into, think about this from our previous limits, that's going to give me 0. Another way is you could look at the graph of y equals e to the x, and you can see as x is approaching infinity, e to the x is approaching infinity. And as x is approaching negative infinity, e to the x is approaching 0. So similarly, if I'm going to look at the limit of e to the negative x as x approaches infinity, that's going to give me 1 over infinity again. That'll give me 0. And then if I do e to the negative x, the limit as x approaches negative infinity, that would be e to the power of negative infinity, which is infinity. And that gives me infinity. Once again, this is something we can also verify with a graph of e to the negative x. So when we do these limits of our hyperbolic trigonometric functions, keep these ideas in mind. It doesn't help, or it doesn't hurt, rather, to keep a graph around. Whenever you're doing these limits, keep a graph of your function around, see what happens. All right, so we're going to find the given limits. These are limits to infinity or negative infinity. And the idea is this, remember, that if you have 1 over infinity, that's going to be 0. And if you have e to the infinity, that's going to be infinity. We'll just kind of work from there. So if I'm going to do the limit of the sinh as x approaches infinity, I'm going to first write out the formula for the sinh function. Then I'm going to look at what I have here, and I'm going to essentially take the limit of each piece. I'm going to take the limit as x approaches infinity of e to the x, and the limit as x approaches infinity of e to the negative x. I'm going to subtract them and then divide that by 2. So this one right here, we know that this one here approaches infinity. And this one here, this approaches 0. So what we end up with is infinity minus 0 divided by 2. Well, infinity minus 0, that's infinity. And infinity divided by 2, what's half of infinity? Yeah, it's infinity. So this final answer here would be infinity. Let's look at it again for the tanh. So keep in mind that limits are, as you know, different than derivatives. You don't have to use a quotient rule for these things. You can split them up. And think of this as the limit of the sinh of x divided by the limit of the cosh of x. Keep in mind that the 2's cancel. When I divide these by each other and use these formulas, the 2's cancel. So I'm going to be left with e to the x minus e to the negative x divided by e to the x plus e to the negative x. Okay, if I plug these in, if I do this limit as x approaches negative infinity, kind of keep in mind what I have. I'm going to have e to the negative infinity minus e to the negative infinity, which is infinity, divided by e to the negative infinity plus e to the negative infinity, which is infinity. And what this ends up giving me is, let's get a different color here. This one goes to 0, this one goes to infinity. This one goes to 0, this one goes to infinity. What we end up with is 0 minus infinity on the top, which is negative infinity. On the bottom, we end up with 0 plus infinity, and this gives us infinity. Well, this form right here, negative infinity divided by infinity, is what we call indeterminate. So it's not going to work. We can't get that to work. We need to do some math smoke and mirrors to get some things to cancel. And I'm going to bring this over here. All right, so I don't know if you remember this. Well, so what I'm going to do is I'm going to write the limit outside and do some math smoke and mirrors. So what I was saying is, I don't know if you remember this, but the last time we were doing limits to infinity, what we did was we divided by or multiplied by the reciprocal of the largest power of the denominator, or the degree of the denominator. So what we're going to do is we're going to look at our denominator and figure out what's my degree. Well, in this case, the degree is going to be e to the x, which is kind of weird. So it's not really a degree. But basically my largest power there is e to the x. So what I'm going to do is I'm going to multiply the top and the bottom function by 1 over e to the x. And again, just keep in mind, e to the positive x is bigger than e to the negative x. So that's why I'm multiplying by 1 over e to the x. Well, when I do that, when I multiply this out, here I get e to the x over e to the x, which gives me 1, and then minus. And then here I've got e to the negative x divided by e to the x, which is going to give me 1 over e to the 2x, or e to the negative 2x. And then I'm going to do it down here as well. So I've got e to the x over e to the x gives me 1. And here I'm going to have plus and 1 over e to the 2x. Now, sadly, and I don't know if you've seen it yet, but sadly, this is going to cause a problem for us because right now, x is approaching negative infinity. So if I plug this in, I end up getting 1 minus infinity over 1 plus infinity, which puts us back into the original situation. So, okay, that doesn't work. So then instead of using my 1 over e to the x, what I'm going to do is I'm going to use my 1 over e to the negative x. All right, I know it sounds weird, but that's what we're going to do. All right, and since I'm out of room, I'm going to clear some space out. All right, as I kind of draw back some boundaries. Okay, just remember, that's how math is. We try something, and if it doesn't work, or if we get the exact same result, we got to try something else. I often think of math as a very large corn maze that someone gave you 2 shots of tequila before you went through it. Okay, so we're going to do the exact same thing, only now we're going to use the e to the negative x. Okay, and again, it's only because we've got this pesky negative infinity. So I'm going to distribute this out. And actually, before I do that, 1 over e to the negative x, as we all know, is just e to the x. So I might as well write it easier first. Okay, so I'm going to end up with e to the 2x here minus 1. And then in the denominator, I'm going to end e to the 2x minus 1. So if I have e to the negative x times e to the x, keep in mind that's like e to the 0, and that bad boy's 1. All right, now let's plug in the negative infinity. If we plug in the negative infinity, I'm going to have e to the negative 2 infinity, right? And then minus 1, and e to the negative 2 infinity minus 1. And this is going to give me, if I have e to the negative infinity, remember this gives me 0, and this gives me 0. Also, sorry, I have a typo. This is supposed to be plus, this is supposed to be plus. All right, next, I end up with 0 minus 1 and 0 plus 1. And negative 1 divided by positive 1 is going to give me negative 1. So this limit here is going to be negative 1. Remember, limits can always be checked with a table of values. And you do have your hyperbolic trig functions in your calculator. Depends on what kind of calculator you have. I just use the catalog to find mine. All right, but this is a calculus class, and in calculus, we take the derivative of these things. So let's go ahead and look at the derivative. So if I'm taking the derivative of the sinh, it's going to be equal to the cosh times the derivative of the inside. So whatever this argument is here, think of that as u, and you can think of this as u prime. So essentially you've got the cosh of u times u prime. Notice all of the derivatives here, they're fairly similar to the trigonometric derivatives. Neat, huh? The only difference is that it's not the cofunctions that are negative this time. It's the reciprocal functions that are negative for their derivatives this time. All right, keep your wits about you. Make sure to have these written down and memorized. Let's look at an example. So I need to find the derivative for the following function. So if I look at this here, I'm going to find the first derivative. Okay, the derivative of the tanh is the secant squared. Keep in mind using the chain rule that when I take the derivative of the tangent, I leave the argument alone, and then I take the derivative of the argument. All right, the derivative of 1 is 0. The derivative of e to the 2x is e to the 2x times 2. Okay. And then the last thing we do is we simplify. So I've got 2 times e to the 2x, and then I've got my hyperbolic secant function with my untouched argument. And that is equal to f prime of x. All right. Think about the chain rule for just a second. I haven't yet set this on video, but I've said it a lot in some of the Q&A sessions I've had with students, so I just want to take a moment to talk about the chain rule. Keep in mind, one way to think about the chain rule is you have your parent function, or what I call the mommy function. And then the mommy function, just imagine that the mommy is pregnant. So when I take the derivative of the mommy, what I do is I take the derivative of the mommy, so the mommy changes, but the baby always goes along for the ride. Okay, I take the derivative of the mommy, but I leave the baby the same. Then I multiply by the derivative of the baby. Okay, this is always the case. So notice in this case, the tanh function, that's my mommy. And the first thing I do is I take the derivative of the tanh, which is that hyperbolic secant, and then the baby doesn't get touched. So here's mommy derivative, baby stays the same, and here is the derivative of the baby. Okay. And of course, sometimes we have pregnant babies because there's chain rule within chain rule within chain rule. For this function here, we're going to find the derivative of the natural log of the sinh of x. Let's go ahead and do that. So let's write down our rules. First of all, as you know, the derivative of the natural log of x, that's always going to be 1 over x, but actually let me write this as u. It's always going to be your arguments on the bottom and the derivative of the arguments on your top. And then the derivative of the sinh is just the cosh. Okay, so the derivative of your sinh of x is just the cosh of x. So let's go ahead and put those together. So think about this as your mommy. What's the derivative of the natural log of something? All right, so g prime of x. What I'm going to do is I'm taking the derivative of the natural log, so I look to see what is the argument. Oh, the argument is the sinh of x. And then on the top, I put the derivative of the argument. And the derivative of the sinh of x is the cosh of x. And then, by definition of hyperbolic trig functions, this is the hyperbolic cotangent of x. And that's my final and simplified answer. For this next problem here, I'm actually going to rewrite h of x into a format that's easier for me to take the derivative. And actually, I'm going to color code it a little bit too. And actually, I'm going to color code it a little bit more. Okay. So when I'm taking the derivative of this function, what I'm really thinking about here is that I've got the derivative. I'm going to do the derivative first of the power rule. And in fact, in this case, my power rule, I've got something to the power of 2. So I know that the 2 is going to come down, the u is going to stay the same, the u turns into a power of 1, and then I'm going to multiply by the derivative of u. But look at what's on the inside. Well, the inside is that hyperbolic cotangent with a funky inside of itself. So I'm also going to have to do the derivative of the cotangent of some value u, and that derivative is going to be the negative hyperbolic cosecant squared of whatever that u is times your u prime. And then the innermost u here is that x to the 1/2 plus 3x. And then the next thing is I'm really just going to use power rules on this x to the 1/2 plus 3x, right? And so I know this is going to give me this as a derivative. All right, so let me just kind of color code this. I'll just color code so we can see which ones we're doing. So the first one is just that purple power rule. The second one is the green hyperbolic cotangent. And then the third is the blue derivative of the inside. Now I've kind of laid out the game plan. So what I want you to do is pause the video here. Pause the video and just write out what you think h prime of x is. Okay, write out h prime of x. See if your instincts are good. On your mark, set, right. Okay, welcome back. Let's see what your answer is. All right, remember, first thing we're going to take the derivative of is this power of 2. So the 2 comes down. 2 comes down in the front. Take the derivative of the mommy. But then I leave the baby alone. So the 2 comes in the front. I reduce the power by 1. Everything inside stays the same. And now I'm going to take the derivative of the inside. But the derivative of the inside is I have to take the derivative of the hyperbolic cotangent first. So I'm going to do that. That's going to give me negative hyperbolic cosecant times whatever's inside. And then times the derivative of the inside. Did you match me? Did we match? All right. Hopefully. Honestly, the most common mistakes I see students make is they take the derivative of the baby before they're supposed to. Notice that the innermost derivative is on the end, right? So the blue derivative, that's on the end. The green derivative, that's in the middle. And then the purple derivative, that's the first one. So notice how this has 3 layers. This is why you have 3 layers of derivatives. Okay, the last thing we're going to do for our derivative is we rewrite it. So negative goes in the front, then 2. And since that hyperbolic cotangent is to the power of 1, we'll just write that next. Then I've got the cosecant, or the hyperbolic cosecant. And then I have this last binomial here of my 1 over 2 square root of x plus 3. And then that's going to be my final answer. If you write your x to the 1/2 as square roots, it'll maximize your points. And other than that, you're finished. All right, good luck in section 3.11.